So, before everyone leaves, we'll please hand in your homework. All right, so let's see. Firstly, next week, Monday is Labor Day, which means there's no class. So, I would like, though, to have, so we don't lose ground too much, that since we have the Friday slot, that we just use that slot to have a makeup class at the same time. Okay? Yeah.
We have our grad student first year grad seminar kind of go.
I know. So I'll tell them the key.
Okay.
And I'll write you an excuse letter.
Or even before that we have a chair seminar.
Right. No, but the chair seminar is at 9.
Yeah.
Right. So we would start at 10:30.
So we have one seminar on the middle process.
Right. It's the TA seminar.
Yeah.
That's the Friday. But let me. I'll talk to them and we'll confirm that. We'll get a note from Epstein's mother. All right. So there will be a problem set 2 due in 2 weeks. Okay, so that's coming and be due 2 Wednesdays from now. All right. What we want to do today, through the next few lectures, is now think about atomic structure a little bit more, and a little bit more sophistication. And in particular, so far, all we've thought about is, in terms of atomic structure, is Coulomb binding. So this was an electric effect. And this is the dominant effect that determines the structure and energy levels in atoms and molecules, or matter in general. Normal matter, that is, of course. One thing we haven't yet talked about and we'll remind ourselves about is the effects of spin. So of course the electron has spin. And you have spin angular momentum, which we often write in terms of Pauli matrices, Pauli operators. So the spin of the electron is spin 1/2. And a question we should ask ourselves and remind ourselves of is, what effect is there on the atomic structure due to the existence of spin? Well, one of the important effects in the context of hydrogen, you have 1 electron. Of course, if we have other atomic species not in column 1 of the periodic table, we have multiple electrons. Of course, the Pauli exclusion principle is going to play an extremely important role in atomic structure. But if we're talking about 1 electron, then there's no exclusion principle to worry about in terms of identical particles. But there is the effect of the fact that we have an intrinsic magnetic moment. So the spin of the electron has a magnetic dipole moment, which is proportional to the spin angular momentum. And if we thought about, just to remind you, if I thought about the electron as a little ball of charge that was spinning around and had an angular momentum S and a charge minus E, classically, such a spinning ball of charge, which has a certain angular momentum, the magnitude of this angular momentum, say, being h bar over 2, would have a magnetic dipole moment. That's a classic problem out of classical electrodynamics. Let's get the weeds out. And what we would have, just classic, if you just solve this problem from classical electrodynamics, you get a spin angular momentum, or you have a spinning ball of charge. It would be the charge times the angular momentum over the mass, and in CGS units, speed of light. Okay? So this would be the spin and angular momentum if I thought about this classically. Let me just look at one thing here. Right. So times the direction of the spin. So let me write this as S over H squared. And this quantity is what's called the Bohr magneton. Okay. So this is what you would say would be the magnetic moment of an electron with that much angular momentum. Okay. Now, in fact, that's not correct. Because it's not a spinning ball of charge. And in fact, it's an intrinsic magnetic moment. And when you look at that intrinsic magnetic moment, you find, in fact, that it has a fudge factor associated with it in order to get the actual angular momentum, or the actual magnetic moment, and this is what's called the G factor. The G factor of the electron. Okay, so we have a magnetic dipole moment operator to UB S units of HY. So if I have a magnetic moment, and of course the charge electron is negative, so really you should have this. The magnetic dipole moment is in the opposite direction of the angular momentum, because the charge is negative. Then in the presence of a magnetic field, we have an interaction minus mu dot B. In the same way that we had the interaction of an electric dipole moment with an electric field as minus d dot E, we have the interaction between the magnetic dipole moment and the magnetic field as minus mu dot B. So the question is what if we had a magnetic field, we would have this interaction with the electric, with the magnetic dipole moment. In the context of atoms, is there a magnetic field at the presence of the electrons? And of course the answer is yes, because the electron is moving, has momentum, angular momentum, and it's moving in the presence of the nucleus. So one can look at this in a couple of different ways. Here's the nucleus, it's in this case the proton, and here's the electron, and the electron is moving around the nucleus. It has some momentum or angular momentum. And in the rest frame of the electron, well, the electron sees the proton going around it. So there is a current loop created by the proton, which creates a magnetic field at the presence of the electron. And that magnetic field then interacts with the intrinsic magnetic dipole moment of the electron. Another way to look at it is to look at it in the lab frame. Let's say that's the rest frame of the proton. And of course, in this frame, the electron is moving. And we can ask, what does the electron see in its frame? Well, we know is that if we have, in the instantaneous rest frame of E, there is B field arising from the nucleus. And if you go back into the depths of your studies and you recall how electric and magnetic fields transform, now generally there's a relativistic correction having to do with the Lorentz transformations, but even in a Galilean transformation, there would be such a field in the presence of the moving charge. And what one finds, to lowest order, in v over the speed of light, the magnetic field in the electron rest frame is minus v over c cross E in the lab frame. In the lab frame, there is no B field. Now this is in CGS units. In CGS units, the electric field and the magnetic field are the same units. If this were in SI units, there wouldn't be a C in there. But then, of course, the force law, the Lorentz force law, is different in CGS and SI units as well. Okay? So, what do we see from this? Well, we see, firstly, that the effects of the magnetic effects are going to certainly be generally smaller than the effects of the electric effects, due to the fact that the strength of the field scales like the speed of the electron relative to the speed of light. So unless the electron is moving close to the speed of light, we don't expect this to affect the coarse structure of the atomic structure. It gives rise to the so-called fine structure. So how big is the speed? What's a order of magnitude or the characteristic speed of the electron moving around in hydrogen atom? Well, we just did that problem for homework. So the characteristic speed well, how would we think about that? The characteristic speed would depend on the characteristic length divided by the characteristic time. So A naught is the characteristic length, the Bohr radius, and the characteristic time is 1 over the characteristic frequency, and the characteristic frequency is the energy divided by h bar. Okay, and the characteristic energy is the Hartree. So putting that all together, we get that V naught is E squared over h bar, or V is E squared over h bar. where E is measured in CGS units. So, what is the ratio of the characteristic speed to the speed of light? It is the ratio of E squared over h bar c, the famous constant alpha, which we call the fine structure constant because it appears in the fine structure of hydrogen. But it's a fundamental unit of electrodynamics. And this ratio is approximately 1 over 137. Who noticed it was 1 over 137 first? I have no idea, but everyone knows it as 1 over 137. And there's some joke with Dirac at the pearly gates and Ascot and the answer is 137. I don't remember the joke, but that's the punchline. So what do we learn from this little exercise so far? Well, what we learn is that the motion of the electron and hydrogen atom isn't really very relativistic, but it ain't nothing. I mean, I'd like to go at a speed, 1 over 137 times the speed of light. That would be pretty cool to see what the heck happens at that speed. Maybe at the spaceport, in a few decades we'll get there. It's down in Las Cruces. But, at the moment, I'm kind of bounded by my Prius. So, although relativistic effects are not big, they're not completely negligible, and we should think about them. Well, how big how big do we expect the effects to be? Of course, the force depends on the Lorentz force. And if this is on the order of V over C itself times the electric forces, then we expect the forces to be alpha squared times the electric forces. So that kind of gives us a sense of the scale of the perturbation. Just a little bit more numerology. We started with when we had our first lecture, we discussed the characteristic units, and we discussed that with an eraser, which I guess is over here. We started with fundamental constants. We had the charge, we had the mass. We were talking about quantum mechanics, so we had h bar. Now we're including relativity, so now we got c. So we can ask ourselves about other scales we can make out of combinations of these different constants. Of course, we have the rest energy. MC squared. Well, we have a new length because m times c is a momentum. And once we have h bar, we have a new length, which is h bar over that momentum. And what is that length? Compton wavelength. Excellent. Somewhere, we like that. So there's all kinds of relations now between the different energy scales that we had in atomic units and other energy and length scales that come out when we include relativistic dynamics. So there's all kinds of little relationships that float around in atomic physics. For example, the Compton wavelength in units, this is really Compton wavelength divided by 2 pi, Compton wavelength bar, is equal to the fine structure constant times Bohr radius, right? Because Bohr radius was h bar squared over mv squared, right? So we multiply by e squared by h bar c, get that. The other thing we see is that the Hartree energy is alpha squared times mc squared. Another relationship. You'll often see the the real atomic physicists will write the energy levels of hydrogen in terms of alpha. So, but instead of thinking about the Hartree, they'll write in terms of the rest energy. All right, so these are some relations. So now, if we want to think about the effects of things like the coupling of the spin of the electron to the magnetic field present at the position of the electron, we have to think about relativistic corrections. And if we want to do that, we need to think, well, what else are we missing if we're going to keep things to order alpha squared beyond the Hartree energy, which is what we argue the coupling of the orbit to the spin is, the so-called spin-orbit coupling. We need to think what else is of that order so that we keep all the terms that are about that order. Now, there's a number of different ways to go about that, and they're somewhat convoluted because it's really hard to, unless we sort of start from the beginning, we can try to bootstrap up and think about the relativistic effects. But it's much more straightforward to start with relativistic quantum mechanics and then make approximations on relativistic quantum mechanics to see what's the lowest order terms in alpha beyond the Schrödinger equation. Now, we're not going to talk about the Dirac equation in this class. If we really want to do serious atomic physics, we really should. And everyone needs at some point in their physics studies to study the Dirac equation because it's a fundamental equation of quantum electrodynamics. But let's just sketch a few things, okay? So really what we want to do, we need to include relativistic corrections in the Schrödinger equation. Okay. So to do that, well, let's just write down the Dirac equation. So the Dirac equation is an equation for electron and positron, thought of as one entity. So instead of thinking about, when we have an electron, we think about it has two components, a spin-up component and a spin-down component. But in the Dirac equation, we have not just a 2-spinner, but a 4-spinner. 4-component spinner. Which is sometimes written as psi A and psi B, where this is up and down, and this is an up and down part, having to do with the electron and the anti-electron. And the Dirac equation is a coupled equation that couples the positron wave function and the electron wave function together. There's lots of ways to write that equation. There's covariant formulation. Let me just write it down in a simple way. Right. So, I'll come to the next board. Right. So one way to write the Dirac equation is, for an electron in an electromagnetic field, and the electromagnetic field is written in terms of the electromagnetic potential. So there's a scalar potential and a vector potential. Okay? So the Dirac equation can be written as following. There's the Hamiltonian, we're looking at eigenstates of the Hamiltonian, so the Dirac Hamiltonian has the following form, which could be written originally in Dirac's original form, C times a vector of matrices, which are called alpha, which have nothing to do with the fine structure concept. It's just another unfortunate use of the same variable for different things. Times the momentum dotted into E over C, times the vector potential, minus the charge on the electron times the scalar potential, plus a vector of matrices called beta times the Bragg mass energy. Okay? And this is times the unit 4x4 matrix, where alpha is the following matrix. It's a block diagonal, it's a block matrix where in each of the off-diagonal blocks are the sigma matrices. So these are 2x2 matrices. So this term couples the electron and positron together. This is off diagonal. And then you have the beta, which is, I don't know if this is right. I'll double check that, seems wrong. The other one, the positron has the negative mass. But anyway, so it's in my notes, I'll check that out. The bottom line is the following. It's a equation which couples through these matrices the electron and positron probability amplitudes together in a single entity.
Does that change at all if fields are quantized?
Yes, indeed. I mean, so this does not include, and we'll get to that, the effects of the Dirac equations. I mean, this would be the same equation where these would become the quantum fields, but the solutions would then involve thinking about the renormalization, including the effects of the quantum fluctuations. And we'll get to that at the very end of lecture today or next time. So the Dirac equation in its first instantiation does not include the effects of the quantum electromagnetic vacuum. These are treated as classical fields. Okay, so now you can there's a whole bunch of algebra to be done where one can write this set of coupled equations for psi A and psi B and eliminate the positron in favor of the electron and plug it back in and just get an equation for the electron. And then expand that to lowest order in the ratio of the energy to the rest mass. So once we do that, if we expand in powers of the fine structure constant, we get the following expression. Let me write it all down, and then I'm going to explain it. Okay. So, what is this expression? This is the Dirac Hamiltonian expanded. This is for the electron alone, having eliminated the positron. And we have the following effects. Obviously, this is the rest energy. That's a constant, and we don't care about it. This, of course, is our zeroth order Schrödinger equation, where the potential energy is the charge of the electron times the scalar potential. Okay? Which is minus E squared over R. Then we have correction terms. And all of these terms, as we will see, and we will assure ourselves, are correction terms of order alpha squared times the Hartree. So this stuff we said was of order Hartree. Right, that's the bare hydrogen atom. And then there's correction terms. And the first corrections are all of order alpha squared. What are these terms? Well, let's look at them individually. So, correction to hydrogen Hamiltonian to order alpha squared. Well, the first term, of course, has something to do with the kinetic energy. So there's a correction. The first thing we have is a correction to the kinetic energy. Well, in relativity, we know that the change in the kinetic energy that's different from what we would have in Newtonian mechanics is to look at the total energy minus the rest mass energy. That's the difference in that is the change, is the kinetic energy. Okay? So what is that? I wouldn't call it that, but I would just call this the kinetic energy. Well, let's just factor this out. We have 1 plus p squared over m squared c squared to the 1/2 minus 1. So in the non-relativistic limit, if the momentum of the electron is small compared to mc, then we can expand this in a Taylor series expansion. And we get that this is equal to p squared over 2m minus an eighth p to the fourth over m squared c squared plus dot dot dot. I guess m cubed. Right? So, this is the non-relativistic kinetic energy. And this is the first correction. It depends on the speed of light. Okay? So what's the size of this in characteristic units? Well, there's lots of ways to take a look at that. We have, if we, so P, the characteristic scale here of correction, we would put in for P the atomic unit of momentum to the fourth power, m cubed c squared, which is equal to, let's write it as p0 squared over m divided by times p0 squared over mc. I mean, there's so many different ways to do this. Let me say it's going to m squared. Okay. This is the hard truth, right? This is P0. What is this? Well, P0, if we thought about this again in terms of the Compton wavelength, then that's alpha times the Compton wavelength. So this, if you plugged it all in, is equal to alpha. So as promised, this correction term is of order alpha squared times the atomic unit of energy. So it's of the order that we had to keep if we're going to include all of the effects of order alpha squared. There's a correction term to the kinetic energy. All right. Let me keep that on the board and erase this. And let's now talk about the next term. What the heck is going on there? So we have what is called spin orbit coupling. There is an effect which couples the orbital angular momentum L to the spin angular momentum S. Where is that arising from? Well, it's really the effect we just motivated this whole discussion with. It has, what I claim is this term is the effect of the magnetic field seen at the position of the electron interacting with the intrinsic magnetic moment of the electron. Let's look at that more carefully. Well, before, what did we have? I claimed that the magnetic effect here was minus mu dot B seen by the electron. Okay? And mu, we said, was minus 2, or 2 mu B times S over H1. And that should be dotted then into the magnetic field seen by the electron. But we just said that that was equal to minus V over C crossed into the electric field seen by the electron. And the electric field seen by the electron is the electric field generated by the proton. So that's the electric field is the charge divided by the distance squared in the direction of the electron. Right? That's the electric field. So I can rewrite this now a little bit. Let me multiply top and bottom of this equation by the mass of the electron. So that mv is now the momentum of the electron. The unit vector defining the unit vector related to the radial distance of the electron from the charge can be re-expressed in terms of the position of the electron by multiplying top and bottom by r. Okay. So what do we got here? Let me rewrite this now. We got 2, we got mu b, let's put that all in, that was e h bar over, who remembers the whole magneton? I should, but I don't. And we got minus p cross r is r cross p. We got another so there's an m squared c squared here. And then we have dotted into s over h bar. And now we have an r, 1 over r cubed. Hopefully I got all the factors in there. I think I did. So, what do we see here? Well, what we see here is the orbital angular momentum of the electron, L. So we have here 1 over mc squared, e over r cubed, L dot s. All right? And what is this? Well, this can be re-expressed if we want in terms of the gradient of potential energy, right? So, I'm going to find, I lost the E here. There's an E over here and an E over here, it should be E squared. So, if my potential energy is minus E squared over R, right? The charge of the electron times the potential. Then 1 over R is equal to E squared over Q. Okay? So, now, that's not exactly what we got. This is not an error. I make lots of mistakes, but this one isn't one of them. Notice there's a factor of 2 here. Thank you, cameraman. And there's no factor of 2 over here. So what happened?
Well, I know about the G factor.
No, it's not about the G factor's there. It's right.
Well, I canceled the 2 from the Bohr magneton.
It's numerology. It's a good point. You know, it's this. The Dirac equation has the G factor in it. So the Dirac equation is correct. But some of the physics we did here was wrong. And the physics that we did wrong here is a very subtle business, in that when I wrote down that I made some very kind of shady remark about B in the electron frame was minus left. And I said something about the instantaneous rest frame, as opposed to just going to the rest frame. The deal is that, well, what we have is the electron, thought of it is in an orbit, is not in an inertial rest frame. It's in an accelerating frame. So there's subtle business about how you transform rotations into non-inertial rest frames. And there is a correction, if I want to think about it. This is all about gyroscopes and how you transform gyroscopes into moving frames. And there's something called the Thomas precession. And that corrects this by a factor of 2, which is in effect having to do with the fact that we're not in an inertial rest frame. So that's why it's better to do it from the Dirac equation, because who the heck would remember the Thomas precession? Not me. Okay, so we got relativistic kinetic energy correction. We have spin-orbit coupling. Again, let me re-emphasize a way to think about this, about the spin-orbit coupling, is that because of the orbital motion, there is a current loop created by the nucleus from the perspective of the electron. And that current loop creates a magnetic moment, and the magnitude of that magnetic moment, due to the motion of the proton, is proportional to L. And that magnetic field then interacts with the intrinsic magnetic moment, the little bar magnet that the electron is. So it's another way to understand this, is that there is an orbital effect which creates a current that the electron then picks up in its little bar magnet. That's spin-orbit coupling, sometimes known as LS coupling. Alrighty.
So you're supposed to prove to us that this is of order alpha squared?
Oh, thank you, Ben. I did forget to do that. I guess let's do that. All right, let's do that. All right, so this is of order alpha squared times the Hartree. Okay? So let's do that together. So the scale here. So L and S are angular momenta. The characteristic scale of angular momentum is h bar. So the characteristic scale here is E squared, h bar squared, divided by mass squared, c squared, times bore radius cubed. Okay, so what do I have here? I have, well, let's see, what should I do? I got E squared over E over A naught squared. That's the Hartree, right? Then I got an E, I got H bar squared, I got an M squared, C squared, and I have another A naught over here. What should I do? Let's plug in for A naught. A naught is H bar squared over M E squared. Feels like I think I have an extra E floating around here and I don't know where it came from. Come back to that. So, cancel this. What did I do wrong? Oh, I know what I did wrong. This is not the energy. Energy is, sorry, E squared over A naught. That's energy. What I wrote down was electric field. So now, try again. I got h bar squared over m squared e squared over, this is good, that works out much better. Because this is the Compton wavelength squared, which is alpha squared times this. So this whole thing is alpha squared. Yay! Okay.
So this dependence on one over r cubed
Yeah.
in units, say, of the Bohr radius,
Yeah.
does that mean that the spin orbit coupling becomes like weaker and weaker for, you know, highly excited states when your average r is really large?
Indeed, absolutely true. So if I were at n equals 100 in the Rydberg series, I would have absolutely negligible fine structures with it compared to what I would have. So indeed, that's good intuition. All right, so we had the relativistic kinetic energy correction. We have spin orbit coupling. What the heck is this? Well, that's something we would never, ever have gotten out of thinking about classical physics and then putting hats on everything. The way we thought about relativistic kinetic energy, or thinking about even the spin orbit coupling. We did this from the point of view, this discussion over here is thinking about classical electrodynamics and then sticking a hat on everything. And maybe we got a key factor wrong or whatnot, but the effect is there, it's understandable. This term, let's see, do we have anything other than midget chalk around? Seems like the answer to that is no. Oh well. C'est la vie. And that's better. Don't throw it because I'll drop it and become a midget. All right. Sorry, a little person. No offense to those inside of this. All right, so what am I saying? Oh yeah, we were talking about the Darwin term. That's what this is called. It's not the Darwin, it's some other Darwin. Maybe they were related, I don't know. But well, what is this? So this is del squared times the potential. The potential here is the potential energy, Coulomb energy associated with the proton and the electron. And then this is then equal to minus h bar squared e squared over m squared c squared del squared 1 over r. Which you will remember is the Poisson equation for a point charge, which is minus 4 pi times the three-dimensional delta function. Okay, well that's what it is. It's something that depends. It's a point perturbation at the origin. There's an 8, so it's got, I know it's a pi over 2 times constants. Okay, so where does this come from? What is the physical origin of this term? It's a complicated business. The original Dirac equation, which we've now erased, is a local equation. The local value of the A and phi of the potential, the electromagnetic potential, couples locally to the electron and the positron. But we got rid of the positron. And in the process of doing that, we made this a non-local effect. So this is a residual effect of the positron. No, there's just no better way to say it, at least that I know. Is it of the order that we said it is? Well, we got it again here. H bar over MC is the Compton wavelength. Compton wavelength squared is alpha squared times the Bohr radius squared. Well, come back to this. Times E squared times the three-dimensional delta function as a function of position. So if we factor out alpha squared times the Hartree, what we have is pi over 2 times that. And this, of course, is the dimensionless three-dimensional delta function. Remember, delta functions have units. They have the units of 1 over their arguments. So a delta function in 3 dimensions has units of 1 over volume. So this is now, so it does indeed get a alpha squared times the Hartree. Yeah.
So this R is, when R equals 0, that's at the position of the proton.
That's correct.
So when we solve, without these perturbations, when we solve the hydrogen atom, we put it in center of mass coordinates. Does that mean that this has to be tweaked just a little bit when you're using it as a perturbation? Because it's R minus, or plus some little tiny amount that may or may not matter because it's inside the proton anyway or something.
It's a good question. I don't really know the answer to it. I've never done that problem myself. I mean, the Dirac equation is an equation for the electron. Now, the fact that we're really in the center of mass, and really it's an equation for the relative coordinate and the reduced mass, how that comes into the Dirac equation, it's got to be in beta and saltpeter. So beta and saltpeter, the famous Hans Bethe, have a book called 1 and 2 electron atoms. Pretty much everything that you ever want to know about 1 and 2 electron atoms is in that book. I'll look there, but I don't really know the answer to that question. All right, so so these are the terms that come out of the Dirac equation that are of order alpha squared times the Hartree corrections to the coarse Schrödinger equation. So let's now summarize. In atomic units. To order alpha squared perturbation. the relativistic corrections are minus an eighth times the momentum to the fourth power. So all, I should all be written, but it's an atomic unit, so it's alpha squared over 8 equal to 4 plus alpha squared over 2, 1 over r dr L dot S. This is all operator plus alpha squared times pi over 2. So that's our relativistic corrections. So the total Hamiltonian is H naught plus relativistic corrections. So alpha is 1 over 137. This is a perturbation. And so what we want to now do is perturbation theory to see how the levels are changed in the presence of these perturbations. So firstly, what we see is that if the orbital angular momentum is 0, this term is 0. So for the ground state of hydrogen, the effect of the perturbations comes in through these terms, and it's some shift, whatever it is. It's some few gigahertz, but it's not very interesting. It's just some other level shift that one can measure and one can think about its implications. What's more interesting is what we see its effect in the first excited state. So let's look at the first excited state of hydrogen. Let's look at the case perturbation for n equals 2. Now, in our description to hydrogen up to this point, we have ignored the spin of the electron, although it's there. It played no role in the energy levels, but there is an additional quantum number which we need to keep track of if we want to fully specify the state. So in the absence of perturbation, so we need to include spin quantum numbers. So for the spin, as we know, we specify the magnitude of the spin and its projection along some quantization axis, right? S is fixed. We only can take on one value for the electron and a half, so we don't carry that around. But we could carry around the m's of S values. So in the absence of the perturbation, the 0th order, our good quantum numbers are the principal quantum number, the orbital angular momentum magnitude quantum number, the projection, which I'll now call m sub L to emphasize that this is the projection of orbital angular momentum, as well as m sub S. So, and the degeneracy now is multiplied by a factor of 2, because spin up and spin down have the same. So the energy to 0th order is minus a half over n squared, with the degeneracy of twice n squared. Remember, n squared was the degeneracy we had in the absence of keeping track of the spin. This is just an extra label that floats around in the absence of perturbation, the spin up and spin down. All right, so now we want to include the perturbation. Firstly, how many degenerate states are there in the n equals 2 manifold. So we have to do degenerate perturbation theory. The n equals 2 subspace has how many sublevels? Well, 8, right? Degeneracy is 8. What are those 8 states? Well, we have the 2s, let's see, L equals 0. And how many states does that are specified with those quantum numbers? Well, m sub l takes one value, m sub l equals 0, but m sub s can be plus or minus a half. So we have a doubly degenerate 2s state. The 2p state, the degeneracy of the 2p state is what? Well, we have, in this case, we can have m sub l equals 3 values and m sub s takes on 2 values, meaning that there are 6 states. 2 m sub s values for every m sub l. Okay? And that's our total 8. So, if we're going to do degenerate perturbation theory, as we discussed, we need to diagonalize our perturbation Hamiltonian in this subspace. Well, what can we say about that? So to think about that, we want to think about ordering our basis in an appropriate way, as we discussed, so that any off-diagonal couplings are kind of near one another in the order in which we write down the basis vectors. And we want to think about what is actually coupled. If I think about these energy levels specified by these quantum numbers, which, if we were to write a matrix representation of this operator, which operators have off-diagonal matrix elements? Well, what we see here is that p to the 4th, consider squared. Well, this is spherically symmetric. Doesn't depend on the direction of p, depends on the magnitude of p. So this operator commutes with L squared, it commutes with LZ. So there are no off-diagonal couplings between states with different L nor different M sub L. It certainly commutes with the spin because it has nothing to do with spin. It acts on a different degree of freedom. So there are no off-diagonal matrix elements of this operator. In the 0th order basis. Same is true for the Darwin term, which is, relative to the origin. Note, Darwin term non-zero only if the electron has finite probability at r equals 0. Because it's a delta function at the origin. So what does that mean? It means that it is only a perturbation on the S states. Only the S states have non-zero impact parameter. All of the other states with non-zero and momentum have 0 probability to be at the origin. So the Darwin term only contributes to S states.
So
Yeah.
what's the relation between the Darwin term and Lamb shift?
Nothing. Yeah. We'll talk about the Lamb shift in a moment, maybe not today. The Lamb shift arises because of the quantum nature of the electromagnetic field. The Darwin term arises due to the quantum fluctuations of the Dirac spinor. So they're both quantum field effects, but one has to do with the quantum fluctuation of the electron and positron. The other has to do, the Lamb shift arises from the quantum fluctuations in E and B, or A and phi.
But if you're going to be calculating a level shift, you should include it, otherwise you get it wrong. I mean, not level shift specifically from E and M.
Well, the question ultimately is, of what order do you want to keep the terms? And is the Lamb shift of the same order as, say, the Darwin shift? The answer is yes. So if we want to really, maybe within a fact, I don't know, I think the Lamb shift is, what is it, 1.1 big, how big is the Lamb shift? Oh yeah, so it's a lot smaller. The Lamb shift is on the order of a megahertz in the n equals 2, and the Klein structure splitting is on the order of 10 gigahertz. So it's a lot smaller. But if you want, if you're doing, obviously we can resolve a megahertz shift. You can resolve a lot better than a megahertz shift. And of course, we'll talk beyond the fine structure next week, maybe during Mickey and Bill's seminar. We'll talk about hyperfine structure, okay, which is even a smaller shift. All right, why don't we call it quits here, and we'll finish this up on Wednesday. And we'll think about Friday. I'll clear it with the instructors or not, but I'll let you know. All right?